transit method, and many more.
So for direct imaging, it pretty much is like direct imaging. So you take a photo of the planet and you use it generally, you use young planets, typically not older stars and planets. And it's very difficult, and even NASA has a hard time using direct imaging to find exoplanets. And yeah, only 46 exoplanets have been discovered this way out of the 4,003 that have been discovered. Around 46.
The Doppler shift. The Doppler shift is a change in frequency due to the Doppler effect. The Doppler effect is the change in frequency or wavelength of a wave in relation to an observer who is moving relative to the wave source. To find exoplanets with this method, you analyze the movement of and properties of the star and planet. When the star moves towards us, the light emitted has a shorter wavelength, so we say its spectrum is blue shifted.
And transit method as well is the method that we used to measure the exoplanets the transits of the exoplanets we did. So it's measuring the amount of light coming from a star, and when an exoplanet comes into transit or lines up in front of the star, that changes the magnitude, and that's how we measure it. We create a chart or graph such as the one over
Right there.
such as the one right there, which is this little oval or indent is when the exoplanet passes in front of the star. And yeah.
And the main transit points are first contact, when the planet first touches the star. And that's called first contact. Second contact is when the planet is fully in front of the star. Midpoint is when it's exactly in the middle of the star. Well, in the middle of it. Yeah. And third contact is when it just touches the edge. And fourth contact is when it finishes going in front of it, and it starts going around it.
So one of the stars that we did was called WASP-2b. It was the second star or exoplanet discovered with the WASP telescope. And this was by far our best graph of the transit. So right here is an image of it without boxcar smoothing, which is technically finding the average of all your data and then putting it into the graph, and that is with boxcar smoothing. Boxcar smoothing helps to get rid of all the noisy images, which is like this stuff, which is unneeded. And I'll also explain this. So HATS 33 was a star that was not recently discovered, but it hasn't really been measured. This graph was not as clean, and as you can see, it had a lot of noise right here and a false peak, which this is the actual peak here. So right here, as you can see right here, this is the first contact, as showed in a previous slide, and this is the midpoint, which is when the peak is at its highest point. This is the this is the top of the peak, the highest point it'll reach in its transit, and this stuff, as you can see, is just all noise. And then, this is relatively just its average. Here.
So we had a lot of trouble in the 4 exoplanets that we did. And we did WASP 103, and that is by far the most bad one we ever had to do so far. And we had bad weather, and we only had 1/10 of the actual grades, so from the data. And the worst part, we didn't even see a transit.
Yeah, there was supposed to be a transit. It had a enough transit.
Yeah, we didn't see it. And for WASP 4B, the observatory took the photo in the wrong place. They thought that the star was right here, when actually it was way over here. And has 33B, lots of interference and noise.
So we want to say thanks to J.D. Armstrong, who was our mentor, Dr. Sutton, who gave us a presentation, and then Dr. Dan Saters, Zach Plater, Mr. Hubble, Dr. G, Ms. Kaiichi, and Mr. Starkey, who is in charge of the observatory in India. So,
Indiana.
huh?
Indiana.
Yeah.
Not India, Indiana.
Yeah.
Yeah, that's what thank you. Any questions? Any questions?
What about the rats? Like you said there was a false peak, but how do you know it was like the real peak?
Oh, because, because that was, let me show you. Yeah, because, this, planet has been observed before, and they know exactly when the peak is.
Yeah, and that's just like interference in the sky.
Yeah, probably just a cloud or something.
Yeah. It was
The
like
actual peak is like that.
yeah. It was this graph. The data hadn't been dealt with yet, so we were like the first ones pretty much to measure the actual transit, and it was not very quick. The data had a lot.
Any more questions?
How do you get noise?
By noise, I mean like, see how this is not a straight line? Yeah, there's like all these random dots, and that's mostly from like clouds and rain
Yeah, from weather.
Oh,
and weather.
How are you convinced that that was a transit?
Because we took data from the observatory, and they said that there's going to be a transit.
Yeah, so this is happening. This data is taken from when the transit was actually happening, and it was observed by Las Cumbres Observatory. And the transit isn't very good, but you can also see that there is a transit there.
Yeah. Any more questions? Thank you.
Moving now to our stellar group, their presentation is titled, How is the measurement of star cluster ages influenced by the stellar evolutionary cycle?
Do not
This
ask
is
questions,
presented by
do
Cindy
not
Kim from IfA
distract
High
me.
School in Hilo, Gabe McKillop from Kalama Intermediate, and Xavier Tablet from Pomoa High on the Big Island. Xavier is a 3-time returnee into our High Star program. Their mentor is Dr. Jennifer Van Saters from IfA and Celeste Jonganilan from here, who is a 5-time. She wins the overall record of the most what should we call you? Repeating customer. Anyway. So good. There we go.
So good afternoon, everyone. My name is Xavier Wood.
I'm Cindy Kim.
And I'm David Doe.
And this is our project. How is the measurement of star cluster ages influenced by the stellar evolutionary cycle?
Before we get into our star cluster data, I just wanted to talk about how we got our data in the first place. So this is a satellite, or a space telescope called Gaia. It was launched in 2013 by the European Space Agency. So far it has collected data for over 1.7 billion stars. And how it collects data is, as it revolves around the Earth, it would pan across the sky, and it would calculate their parallaxes to find the range of the distances between the various stars.
Okay, so our project focuses on star clusters. So star clusters are groups of stars bound together by gravity. There are two main types of star clusters, and that's globular clusters and open clusters. Globular clusters appear to be more dense. They're older, or relatively older, and they contain, the stars that they contain vary in ages and composition. Whereas in open clusters appear to be more spread apart. Most of these are considered closer, and the stars that they contain share similar ages and compositions.
So what we did was we took data from the Gaia Data Release 2 catalog, and we used a program called TopCat, which allows us to make all these like really cool looking graphs. And so we did was first was we took one of the clusters. This is M67, and we put it into a 2D plot, which graphed right ascension versus declination as right here at the top, and we graphed it using density. So as you can see, the darker color that's highlighted in this black circle is where the M67 cluster is, and everything else around it are the background stars. And so in order to get rid of the background stars, we would need to plot it into a cube plot, as seen here, which is three-dimensional. So you have your proper motion right ascension, your proper motion declination, and you have your parallax. So proper motion is the star's movement through space, and the parallax is the distance from Earth. And what you see is that the background stars are concentrated around 0, 0 in that dark area, and the M67 cluster is that dark spot there. And from that, we isolated the cluster as a subset, and we plotted it onto an HR diagram, which is a Hertzsprung-Russell diagram, which graphs brightness on the y-axis and color on the x-axis. So the farther you are, the farther the star is from 0, the more red it is, and the higher up on the y-axis you are, the brighter the star is. So you would find your type A, type O, type B stars up here, and you find your type M, type K stars down here.
Right, so this graph is primarily focusing on the isochrones and a couple of star clusters that we chose. So these are the isochrones, these colorful lines. And what an isochrone is it's a graph where a line would be drawn through stars with the same age but various masses. So the green isochrone would be 19.9 stars that are 19.9 billion years old. The black isochrone is 44.7 billion years old, and the blue isochrone would be 100,000 years old. So, and then these are the star clusters. So M67 is around 3.5 to 5 billion years old. So it would kind of follow the green isochrone, but since it's not exactly the same age, it's a little shifted, but it would be in the general area of the isochrone. And Mercury 59 is around 1.25 million years old, and it would follow the black isochrone. And even though the black isochrone is all the way over here and Mercury is right here, it's because
because the galaxy is so young, star cluster is so young, there would be a lot of interference, and that would cause it to shift more to the right. But without the interference, it should fall out and be black, basically.
Okay, so here's another HR diagram that we did. And so I graphed M42, which is characterized by these red stars right here. So M42 is about 1 million years old, and it should be following the purple isochrone. And you're wondering why isn't it exactly on if this tail, part of the star graph is right here, and it almost nearly follows the shape of the isochrone. The reason why it's shifting to the right is because it's so young. Because it's 1 million years old, you still have a lot of the gas and dust that's left over as the stars are being formed, and that causes interstellar reddening effect that causes the HR diagram to be pushed more to the right of the graph.
Okay, so this is another cluster we should also look at. This cluster is about 4.26 million years old, so in log age it's about 6.64. You can tell that it's following the trend for a cluster that would, or the model for a cluster that would be about 10 million years old. So it's, there is some, the reason that it's not exactly a nice cone is because they're just models. So they're not necessarily going to follow the model exactly for every cluster. And also, since it's not exactly a million, not exactly 10 million, it wouldn't necessarily be in the middle. But you can tell that it's following the trend of where the age range should be. Okay, so this is another one. This is the cluster right here, and this cluster is about 7.4 billion age, or about 27 million years old. So this is these are the isochrones for around the age range of this cluster. As you can tell, it's following the pattern is the same, but this one is also shifted slightly to the right, which could be attributed to interstellar reddening, like we were talking about, or also the method that we use to select the members for the cluster. There might be some error. Yeah, so that could be attributed to that as well. This one looks really nice. This one is about 12.6 years, and so this is the isochrone for that age range, and you can tell that the model fits with the data very nicely here.
This graph also shows that where figuring out the age of star clusters kind of hits a roadblock, because from 4 billion years on, the HR diagrams for clusters start to not change that much, because as stars move up, burn hydrogen on the main sequence, there's this turn off here, and there's a certain point where you get to a later spectral type stars, which their life cycle is extremely long, in the billions and even trillions of years, and at that point you don't really see any movement on the graph, which makes it really hard for us to determine, what's the difference between 4 billion years, 10 billion years, even, and so on and so forth. And so that is something that we would want to try to look forward into. How can we get past that in the future research? So why is this important? So studying stellar clusters is important because if you look at individual stars on their own, you can't really tell their age. Like even our own sun, we figured out our sun's age by looking at by analyzing meteorites that landed on Earth and doing radioactive decay on it to see how old our solar system was. But when you're looking at stars such as these clusters that are between 800, that are from 800 parsecs and on, you can't go out and take a sample of what's around the stars. And so the good thing about analyzing stellar clusters is that these stars are all in the same area. especially with open clusters that were, these stars were all formed at the same time, the same age, out of the same material, so they have the same composition, and they're formed at the same time. So what we can do with this is, if we find a cluster that has the same, has stars that has the same composition and age as our sun, we can actually better understand what is going to happen to our sun in its future.
We would like to give a special thanks to Dr. Van Zaders for providing the data and the expert knowledge for us to allow us to continue on this project.
I'd also like to thank Celeste Jongenelen for helping us further understand the concepts.
We would also like to thank the European Space Agency for making the Gaia Space Telescope to allow us to gather this data.
And we would like to have we would like to issue a special thanks to Dr. Armstrong and all others who have made this year's High Star program a possibility. These are our sources. Are there any questions?
You mentioned the evolution of stars and using that to tell what's going to happen to our sun. Is there a way to do like spectroscopy or color data stuff to see what gases are in stellar clusters? Use that.
So if we can use spectroscopy to figure out what gases are in stellar clusters, yes, you can. I heard some group, or if you, especially with like, the materials actually change over time, even with globular clusters, they're older, so it's kind of like a self-enriching effect that happens over time, that as stars die, the gases that are expelled off of these stars are picked up and formed into other stars, and that could be a way to further this research. Are there any other questions? Not. Thank you for your time.
We're moving further out into the galaxy now. Our next group is our galactic group with their presentation, Does an Active Galactic Nucleus Affect Star Formation in a Galaxy? Presented by Kai Winterly from Walkersville High School in Maryland. He's a 3-time returner. Aiden Chun from Roosevelt High School on Oahu. He's a 4-timer. And Annika Encheta from Yale Intermediate. Their mentor is Dr. Jenny Shi from Maui College here. Okay, guys.
All right, so we did does an active galactic nucleus affect star formation in the galaxy?
I'm Aiden.
I'm Kai.
And I'm Monica.
All right, so we chose to do this topic because over the course of the past year, Aiden and I worked with MANGA data, and Annika did supermassive black holes. So we kind of fused those together to make this. And our motivation was to further understand how supermassive black holes work and how they affect the galaxies around them. Okay, so for definitions, our active galactic nuclei, or AGNs, are the supermassive black holes that exist at the center of all galaxies. So that's like our main subject. So we've also got star formation rate, or SFR, which is the rate at which a galaxy produces new stars, and redshift, which is basically how objects that get further from Earth shift towards the red spectrum. Luminosity, which is the total amount of energy produced by the surface of a star. And then there's flux, which is the intensity of a star that is observed by us. So it's luminosity from our perspective. And then the accretion disk, which is a disk of gas and dust that orbits a black hole that emits a lot of heat and energy. So we hypothesized that the AGN would have a lower star formation rate than a non-active AGN. And that we hypothesized this because the accretion disk of an AGN produces so much heat that it heats the gas around the galaxy and prevents young stars from forming. So for our data, we used MANGA, which is mapping out nearby galaxies at Apache Point Observatory. And they work with SDSS, which is Sloan Digital Sky Survey. And that's an online database of a lot of astronomical data that's free for anyone to use. And what they do is they use about 127 fiber cables to make a 2D map of observed galaxies, which provides a lot of various sample data that's helpful for finding correlations between celestial objects.
So going off of what Kai said, the manga data provides you with, oh, by the way, they're not the Japanese comics, so, but they instead study the spectral data that comes from 10,000 nearby galaxies. And the way that we use these, or they come in the form of data cubes, which are three-dimensional arrays. Two of these dimensions come in rate ascension and declination. You think of them like X and Y. And the other dimension comes in the form of wavelength. We then examine the flux data on emission lines, specifically H alpha, for each pixel. So as you can see, like each of the circles over there on the galaxy. We got our sample of galaxies from a paper from Rembold at 2017, where he matched galaxies with active galactic nuclei with non-active galaxies based on their stellar mass, redshift, morphology, and inclination. We selected 20 of these pairs, and all of them are spiral galaxies for consistency. In order to get our calculations of data, we follow these steps over here. So the first step is that once we get our data cube, we open it up on Jupyter Notebook using Python. And from that, we define what kind of data we're looking for. So in this case, it would be stuff like flux or wavelength. Afterwards, we make a mask to mask the center of the galaxy where active galactic nucleus influence could be strong. So as you can see here, this is the mask that I made. And then after that, you find the flux in the H alpha line across the galaxy. And using that, you calculate the luminosity in the H alpha line and the star formation rate. You then compare this data with other galaxies and make it presentable. And then we're done with this project. Over here is the code. So over here, it takes in the manga ID, which we got from our 20 pairs, our sample. And from that, it gives us the plate IFU and the redshift. So we use the plate IFU to download the data cubes and the redshift in our calculations. And over there is the code that we do our calculations with. So that top part over there deals with opening up the file and defining what data we're looking at. So you can see like where there's flux and then wavelength over there. The second part is defining what the center of the galaxy is, X center and Y center. And then this chunk of code right here defines our mask that we mask the center with. And then the rest is used for calculating the luminosity or recording the H alpha emission flux. And then calculating luminosity and the star formation rate. To do our calculations, we use these equations over here. Because for this one, we use this because redshift affects the light from the galaxies that we're observing, and it pushes them to the right end of the spectrum. To account for this, we use this equation to get something called the rest wavelength, which is the wave, the light from the galaxy that's not affected from redshift. We also use redshift in Ned Wright's cosmological calculator to determine R, which is the luminosity distance between us and the galaxy we're observing. We then multiply that by the flux in the H alpha line and fortify it to get our luminosity at H alpha. We then multiply this by 7.9 times 10 to the negative 14 to get our star formation rate. We got this relationship from Kenneth in 1998.
Okay, so as you can see from this graph, as the title states, it is a comparison of the active galactic nucleus's star formation rate versus the non-active galaxy's star formation rate. So as you can see here, the blue represents non-active galaxy's star formation rate, and over here is the red dot, which represents the active galactic nucleus's star formation rate. So as you can see here, the trend lines for the two are very close to each other. And so this means that there is no obvious correlation between having an active or non-active galaxy nucleus and the star formation rate. So on the x-axis is the stellar mass, which is the stellar mass of the galaxy, and the y-axis is the star formation rate, which is how many solar masses per year. We also found that as the stellar mass increases, as you can see, the star formation rate increases too, meaning that the larger the stellar mass is, the more stars you're going to see in a year. So, in conclusion, in the face of our data, our hypothesis is proven false. Instead of finding that star formation rates are decreasing with active galactic nuclei, we concluded that there is no obvious connection between the two. Some reasons our data doesn't show any correlation may be because the heat from the accretion disk may not be enough to stop star formation or at least slow it down, or perhaps a miscalculation of luminosity and misplacing the mask, or too small a sample size with too many variables to account for. To further this project, we want to refine the way we observe and analyze the data used. We initially masked the center to block out parts affected by the AGN, but another way may be more accurate. Another thing we want to do is remove mass as a variable between non-active and active galactic nuclei. And we also want to reanalyze data and possibly get more. Are there any questions?
What's your definition of a spiral galaxy?
It's a galaxy that is, it's very disc-like in shape, and then it has arms that kind of looks like it's spiraling. An example of that is
Right there.
Yeah.
The Safer Galaxy NGC 1566. So you can see.
That's cheating.
Why did you choose NGC 1566?
Because
That's cool.
it's a Safer Galaxy, which has an active galactic nucleus.
Ah.
And
But do you have any personal connection to it?
I'm sure it is a very nice galaxy.
Very much so. Isn't that the one you're monitoring?
yeah, this was the one that I was measuring the supermassive black hole's mass. Any more questions?
About the mask that you made, is that black square of the mask or is the whole thing a mask?
Okay, so if you so the black area is the mask. So that's where we would be covering up, and we won't be calculating the luminosity and star formation rate. So yeah, the black area is where we'll be covering.
It's basically just cutting the galactic nuclei out of the equation So like that's just taking out the data that's coming from that, so we can actually measure the space around it, which is where the stars are being formed.
You can think of the black area as the area where we're going to cut with, scissors for a second.
Any more questions?
Thank you.
Boomerang right back into our solar system with another exoplanet group. The title of their presentation is called Observing Mercury and Venus as Exoplanets. This is being presented by Jordan Vaughn from Maui High School, a four-time repeat high star student. Zach Teagarden from Phillips Exeter Academy in New Hampshire. Scarlett Howell from Iolani School on Oahu, and Sierra Ryden from Elphinstone Secondary School in Canada. And both Zach and Sierra are two-time repeaters. Their mentors are Dr. Zudon Sun from IfA Maui and Zach Clater, who is a fourth-year grad student, right, at IfA.
All right, hello, I'm Jordan.
I'm Scarlett.
I'm Zach. I'm Sierra.
And our project is treating Mercury and Venus transits as exoplanets. So to start off, Mercury and Venus are the two inner planets within our solar system, Mercury being the closest to the sun and Venus being the second one and also the hottest. We were comparing them to exoplanets, which if you don't know, exoplanets are planets outside of our solar system orbiting its own star other than our sun. There are multiple ways to detect exoplanets, including astrometry, Doppler shifting, direct imaging, and the transit method, which is the most common method and the method that we use. The best way to describe the transit method is if you will look at this picture here. You have the planet go right in front of that star, and as it goes in front, it'll block some of the luminosity, causing a dip within the light curve.
Okay, so Python is a programming language that is very popular among astronomers. So we use Python to gather BITS images from a database. BITS stands for Flexible Image Transport System. And basically we created an algorithm that searches a database for pictures of the sun at a specific time that would have Venus and Mercury transiting in front of the sun.
Astronomy is like the Freddie Mercury of sciences. Most of astronomy fills our soul, but not our plates. That's a quote from GD. Our project was to observe Mercury and Venus as exoplanets. To do this, we calculated the transit depth of both Mercury and Venus using a light curve imaging and calculating the size of the planets.
So here's our hypothesis. Because Mars and Venus are so close to Earth, so if we look at them as exoplanets, that the transit will be visible and accurate to what their properties actually are.
So here goes our method. So this is the first step to finding Mercury and Venus transits. We use the heloviewer.org, and what it does is it shows sun and a visible light in HMI, which is a highest-mo helioseismic magnetic imager. And as you see right there, can anybody tell me where Mercury is on this picture? Yes.
Is it right there, kind of like at the bottom right?
You are correct. That is Mercury. So as it'll go across and it'll give us our nice transit. So we took the dates and we took the time and we went to a website called JSOC, or the Joint Science Operations Center. And it gave us all the data for all the days that we put in. So what we did was we took the first day, the second day, and the third day. The first day is before the transit, and the third day is after the transit. And each one of these peaks is a day. Can anyone tell me where the Venus transit is in during this? Does anybody know? Yes?
It's the drop after the second peak.
Yeah, so it's right there. Okay, so if we zoom into that specific section, you'll notice that unlike our pretty picture that we had in the beginning, This transit is slightly tilted horizontally. And this is because of the instrument that we use, so we want to completely get rid of that, and we want to normalize the light curve and make it a nice horizontal line. Oh, also, we use the continuum data, which is basically giving the intensity of the light over images in 45 seconds. So each image that you see is taken every 45 seconds.
Okay, so this is how we did it. We have 30 days of data in 3 columns. Day 1 before transit, day 2 during transit, and day 3 after transit. Because you can see the graph on the last slide is like a curvy, like that. It's because the instruments, it orbits around the Earth. So we don't want a very curvy data, so we want to normalize it. So we want it to have a straight line, and with the transit, you have a dip. So for the average brightness, say it orbits the sun, and no, orbits the Earth. So we had the day 1 and day 3 data combined together, and to find the average brightness. So that's the average brightness of the sun observed by the Earth. So from the day 2, we divided by the average brightness, it was subtracted by the average brightness, we got the difference. And to normalize it, but normalizing would mean we want the thing, so we want the brightness to be like 1, so to be a straight line. That's called the normalized, that we can see just a dip without other curved things. So here's our graph. It's a beautiful curve.
Much different from the one you saw before.
So this is the calculated transit depth. So depth is about 0.0015 in brightness. So our hypothesis was we thought that the calculation right here, so this is actually the size that was on the image, like the sun. So we have calculated that using this equation. We have the depth of the transit. So we put it in, and we got a radius. But we were wrong at the beginning, because here we can see this is the spot on the sun by the transit, the shuttle. It's not actually the size of Venus, because Venus is between Earth and Sun, and they have like certain distance. That the thing we had is actually the shuttle of Venus that is much bigger than actual Venus size. So we used the triangle magic called trigonometry. So we use geometry. So this is the 2 similar triangles. The actual radius of Venus over the sun, the distance between Venus and Earth is proportional to the shuttle of Venus here, the radius of this part over this distance between Sun and Earth. So we had this equation and used a trick. We had calculated the actual size of Venus. So it's about 6,527 meters. Not meters. So this we compared with the actual size of the Venus radius. Mercury right was being 10%. It's not Mercury.
Oh, okay. So we created transit visuals. So basically we used Python to create little like movies of the transits. So basically this code right here, it would search the database for the images of the sun, and then it would put them all together into one GIF that we could basically visualize the transits of both Mercury and Venus. And we can go ahead. You can see right here, this is Venus. So we created this with Python. And then here's Mercury. So you can see Mercury is very tiny, and Venus is much larger, so I was going to get the transit, but with Mercury we actually could not get the transit because its transit depth was so small. We couldn't even see it on the light curve, because right here you can see just how tiny it is. There's 0.000, 4 zeros and then a 1. So with Venus it was 2. So this is less than 1/10 the size of a cell. And that is just way too small to see among the noise of the solar radiation. So it was too small to see Mercury's transit.
To get the depth of the transit of Mercury, we used the transit depth equation.
which is the radius of the planet over the radius of the sun squared. And we came up with the number, the depth over there.
So in conclusion, the actual size of the planet is much smaller. The shadow of Venus on the sun is a lot bigger than the actual planet, and we had calculated it to be within 2% correct or 10% error, so it works.
And Mercury's transit could not be detected, but we were using equations to calculate the size of Mercury just from what we could see in the images, and we measured the pixels and we were converting it to kilometers using triangle magic and things like that. But sadly, we couldn't figure it out, and Dr. Sun actually figured out what's going wrong with the equations, so we are going to be working on that.
So what we would like to do next is we would like to use duration to figure out the orbital distance and the orbital period. Since we already used the depth, we want to know, like, as it transits, can we find the orbital distance and the period? And we'd also like to compare these transits with an upcoming Mercury transit coming in November. And we would also like to finish the calculations of Mercury, as he said. So I would like to give special thanks to J.D. Armstrong, Dr. Sun, Zach Clater, Jeff Matthews and Mike Nasser, Mary Ann Cadota, Carolyn Kaiichi, Mr. Hubble, and everyone else at the High Star organizations. We love you. Thank you for making this possible. Thank you very much. Any questions?
What is solar granulation?
It's like the noise that we see from the sun. You can see like the sunspots and things like that. So basically, we can't really yeah, we can't. This is just like the noise from the sun, so we can't actually.
He's asking what's the clarification. That was really good. Anyway. Yeah, any other questions? No? Okay, thank you.
There's no High Star program. So unfortunately, we have another hour before our refreshments come. So does anybody want to do their presentation over? I mean, I didn't understand some of it, so.
Just do it again.
We have to do
I'll bring out last year's.
Otherwise, yeah, I guess we'll kind of just mosey on back to the other building, and you guys can clean up and do some last minute things, and we should be receiving our dinners about 4. So please stay for refreshments, because there's a lot of food coming. Be healthy. Thank you.
Yes.
We could, because I have a slideshow.
You want to do it? We have one more, we have a student here that would like to volunteer to give one more presentation. If everyone's interested. All right. And if you'll give me just a moment, I think I may be on the verge of setting up a microphone. Ooh, we're getting into really high tech here. No,
Oh, okay.
Oh, yeah.
I updated. Yeah, this is the problem. I didn't do all by transit.
It's like a couple rooms down.
Yeah, because I didn't want to see this. And then like every building I did,
Check, testing that. Good. Check.
Big Smash has that tournament.
like 20 players.
Okay, JD, you ready?
Yeah, go ahead. Let's see
Okay,
here.
a serendipitous discovery of a transiting body.
Okay.
So,
Oh, that sounds.
do you want an introduction here?
Yeah, okay.
All right, so, ladies and gentlemen, Sierra and Zach and Sierra have been working with me for a few years now, and they had a really amazing project. Sierra had to move to Canada for at least a year, and Zach was able to get the project into the science fair, but Sierra was not. And so I think this is sort of Sierra's way of going, hey, I want to make up for that, for not getting into the science fair. And I really appreciate it. So thank you. Let's give them a nice welcome for their second.
A transiting body is a transit it's defined as a visible passing of an object in front of its host star.
So basically, we detected a transit around a star that had not been known to have any exoplanets or objects in orbit of it. So we identified the object that we see transiting as an exoplanet or a binary star.
Exoplanets, some of the main ones are hot Jupiters, super Earths, mini Neptunes, hot Neptunes, and super Jupiters, and rogue exoplanets are also ones that don't have a host star.
And exoplanets, like you've heard before, they were discovered using the transit method. Basically, this graphs the intensity of a star on the y-axis over time, which is on the x-axis, and you can measure the intensity lost from the star as the object passes in front of it from our perspective.
The other option of what this object that we discovered could be is a binary star system, which is two stars that orbit each other.
And we also use the transit method for this. So yeah, this is what a light curve of a binary star looks like. You can see like it's a repetitive pattern where it goes further down and then it dips in the middle slightly less, and then it goes down. It looks more V-shaped and it's much harsher than just a very kind of concave exoplanet transit.
Doppler shifts is one method to detect exoplanets, and it's changes in wavelength that's affected by gravitational pull upon a star.
So we observed the stars using the LCO network of telescopes, and we used MIRA AL, which was mentioned before, and that's what we used for photometry. And we used the transit method for observing the star. This is a picture of MIRA, so you can see this isn't actually like our image, but this is just a picture of what MIRA looks like. This is the program we used to get the photometry.
So the serendipitous discovery. So we were observing another exoplanet, a known one, just confirming it, and but the check star that we used, it messed up our data very much, and the reference star, and that we at first thought we'd done something wrong, but then we looked into it and it was something else.
Yeah, so this is kind of what the light curve looked like. It looks kind of like a mix between an exoplanet light curve and a binary star light curve. So we got more observations because we were interested by this, and we confirmed it. It didn't seem to be an error in the data or a cloud or anything. It looked like, according to JD and our research, it seemed to be an exoplanet or binary star transit. So we got more observations, you can see on this graph, and it looks kind of like you might be able to see another, like the beginning of a transit in that maroon color. This isn't all of our observations, this is not up to date, but yeah, so it looks like there's possible activity, and it looks kind of like the star is variable. Like the base magnitude value varies a lot, so that's why we thought it might be a variable star, and it was listed as a possible variable star before, but we think that this actually might just be changes in sight that we view from, and also weather and things like that. I do not think that it is variable star. So yeah, you can see that's our first transit, and then all the way to the left on the second graph, that's our first transit just smushed.
Various pole stars. They don't have a set magnitude value, so they vary pretty much. And when we researched for the star in the database, it was listed as it could be possible variable star-like exit.
Yeah, so the binary star-like transit. You can see the reason that this our actual graph goes up instead of down is because these are in different measurements of brightness. So on the right are our transit, that's in magnitude. So the higher it is, the actually fainter it is. So you can see it looks kind of like it has that binary-like transit where it's very spiked. So that's why we thought it might be a binary star. So we decided to kind of look into that more. Oh wait, no. Oh, it would be impact. Okay, well, I'll explain this. So impact parameter, basically it's a measure of like how far from the center of the star the transiting object is, and we think that if it is an exoplanet, the impact parameter is basically like very high or very low, transiting very high on the star, very low on the star, from our perspective, because if that was the case, then it would make sense that it would be more V-shaped rather than very concave, because it would be spending less time transiting the star. Okay, so these are some of the calculations. So these are just some of the calculations. I mean, magnitude 1 minus magnitude 2 equals negative 2.5 log to the 10 times density 1 over intensity 2. That's 0.07. We basically kind of rearranged these equations to get the radius of the object we were looking at. And it was basically 2.1 times the size of Jupiter, which is the upper limit for an exoplanet in orbit of this star. Yeah, radius of Jupiter. So basically like 2.1 times the size of Jupiter, but it's a lowest possible thing that a star could be in orbit of this star.
Conclusions. So we need more observations. We've only captured one full transit of this, and so we need more observations to determine what this object really is.
Yeah.
And the math is estimated, and we did a calculation, but in order for that calculation to be correct, it needs to be an exoplanet. If it's a binary star system, that equation isn't good.
So yeah, basically that's kind of our thing. I don't know if there's anything else. So thank you for listening. If you have any questions, this was not rehearsed at all, basically. So I'm sorry. And, yeah. The equation is correct, regardless of whether or not it's a binary or exoplanet. No, it is. Because we're just measuring the size of it to see which one it was.
It has to be a hot Jupiter,
Yeah, it would be a hot Jupiter,
isn't it? Okay.
So it sounds like this is an older presentation. Since
Yeah.
then, have you guys gotten more observations?
Yeah, so we have a lot of new data, and now that Sierra's back, we're both going to look at it on Monday, I think.
Starting Monday if you want, yeah.
Yeah, we just got a ton of data, like, yeah, got a lot of data.
Which way are you currently leaning, exoplanet or binary star?
I'm hoping exoplanet, but I'm not sure really.
It's hard to say.
When will you guys know?
When we get more data, or when we have more data, we'll be like, look at the data.
Okay.
Yeah. Okay, cool.
Okay, so since Sierra did not get a chance to enter the science fair, we've got the judges here, and how many think he would have won an award at the science fair?
No.
Oh, most definitely.
Yeah, I got
Yeah.
it.
Air Force
Yeah.
a backpack.
Okay, so Air Force backpack, we have an Air Force backpack. Who would say maybe third in physics?
Yeah, I got third in space.
Yeah, at state level, Zach got third. No, just the Air Force Award then, right? So the high star, for the high star science fair, you get the Air Force Award.
Thank you.
Let's give them a hand.
Take select. You want to present our community one? Community one? You want to do your hypervelocity stars?
Fault in Our Stars too.
Fault in Our Stars
Do
number
it.
three.
I don't remember the one that was in the Fault in Our Stars, but I mean, I know the presentation.
I hardly remember any words that I put in Fault in Our Stars. I don't like those.
Let's wing it.
Okay.
All right, can I just just quickly
Okay,
glance through
here's this
Lucas's
event
thing?
that's
Yeah.
definitely in
I'll just be
town.
like, this is Lucas. Lucas.
Oh, wait, there's like an
Well,
event
Lucas,
flyer
you
that's
could
really
say
fast.
Lucas is where Lucas is,
Lucas is Lucas, and
Yeah.
that is Lucas.
and you know what he's doing. He's over in Manoa,
Yes.
going to UH.
Okay, so what Lucas did, he's not here, he's in Manoa, is he observed a reflect. Yep. What I did was I measured the properties of a planet candidates using Kepler's third law, the planetary equilibrium equation, and the depth equation to see if they were habitable. And Celeste?
I used, so the Star Cluster group used Gaia's second data release. I actually used the Gaia's first data release when it had just come out. And I used it to find something called runaway star candidates. I'll get this.
That's Lucas. That's some more Lucas. Oh boy, Lucas. Oh, Lucas. Star Wars.
Image credit, Lucas.
Here I am. Okay. So hello everybody. You've known me from before. My name is Jordan. At the time I was in grade 10 and now I'm a senior, so this has been quite a while since I performed this. So cut me some slack here. And my project is called Take Me to Your Planet, determining the habitability of exoplanets. So, you've seen this picture already. It was made by our lovely Space Jam, aka Josh. And from the previous project that I presented earlier, an exoplanet is a planet outside of our solar system that orbits its own stars. And there's the same picture that I used in the other presentations because I really like that picture. It's really good. So what I did is I joined a program called HiStar, many years back. What is HiStar? I don't know. And what I did was I was working with two other students, Alan and Stephanie, and I was looking at hot Jupiter planets. But you know, I wanted to find something a little more down to Earth. So I decided to look at Earth-like planets. So what I did was I looked at thousands of light curves for multiple K2 campaigns, and I finally settled on 27 from a paper by Pettigera et al. So my hypothesis was since 1 in 5 planetary systems is likely to have an Earth-like planet, and thousands of planetary candidates were found in the Kepler data, then Kepler data should contain Earth-like planets and hundreds of them, which should be able to be found easily among planetary candidates. This is a paper, Pettigrew et al. It was a nice read. I enjoyed it. So what I did was I took data from the ASA archive and I converted them into a .text file using Python, and I was able to graph the transits by folding the light curve, which would allow me to find the period. So unfolded, folded, unfolded, folded. So the first thing I did was I wanted to find how deep these transits were. And I used this using the depth equation, which is the radius of the planet squared divided by the radius of the star squared. And this will also help me find the planet radius and the stellar radius. As you can tell by this nice graphic made in MS Paint, the tiny planet will cause a smaller dip, and the bigger planet will cause a bigger dip. Wow. So then I used Kepler's third law. And this helps me find the orbital distance, also known as the semi-major axis. And this is the quantity of the period of the planet squared divided by, or times, the mass of the planet divided by the mass of the star, which is then divided by Earth's period, which is 365 days squared, to the 1/3 power. Kepler, thank you. And then I used the planetary equilibrium equation, because as you know, kind of need water, right? So I've had to figure out how hot these planets were, if they were sweating like in a manga, or if they were really cold and, cool sun. And so how I did this was I used the temperature of the planet is equal to the temperature of the star, the quantity of 1 minus the albedo. Albedo is how shiny something is, so it'll either reflect light and make it seem more light-like. To the 1/4 power, square root the radius of the star divided by 2 times the distance. And as I was looking through all my data, of the thousands of light curves, none of them were habitable. And I was like, why? Why is there no Earth-like planets? And I thought this was because they're a lot harder to detect than large gaseous planets. I was looking at more more sun-like stars, and tiny planets such as Earth size aren't really going to show up. Kind of like how Mercury was with earlier, you really couldn't see even though it was really, really close. So me trying to find something small really, really far away against a really big star is not going to work out. So I was able to find gaseous planets more easily. So my next step, wow, the Bulbasaur gift. You can really tell who likes to decorate slideshows. I would like to find the planets' compositions and masses using radial velocity and find more planets and then publish my findings, which I did do a follow-up at my last year's science fair. It was great. So my project for this year, I had a mentor named Sam Brunblatt, and he was amazing, and I loved him. And there's JD and me, and I'm really happy. That's not often. And then there's my teacher at high school. His name is Keith Amadas. Yep. That was, why is that not showing? Okay, well, it shows on here. That was High Star. Now it's dark and black. You can't even see it, that's sad. Okay, and then that's my family. On top of Polyalphala, and I was cold. Here's Celeste. She's gonna do a lot better now.
Okay. Yeah, this was definitely less of the sciencey one and more of the public presentation, but I had called it Star Light, Star Bright, the fastest star I see tonight because of the old nursery rhyme. I was a senior at the time, now I'm just aging. I know. I'm a college student now at Lewis St. Clair College. So basically, I guess I'll start with what is a runaway star. Runaway stars form when you have a binary star system, so 2 stars opening each other. And what can happen is one of the stars can actually explode and become a super.
I know. I feel you.
I have forgotten everything about this presentation. But basically, it can explode, and that causes the other star to be ejected away. These stars, I think I do want to go ahead clusters. These stars move away from the system pretty fast, but not as fast as hypervelocity stars. I did. Okay. So hypervelocity stars are similar formations, 2 stars that orbit each other, But instead of having a star explode, what happens is the one star is actually captured by the supermassive black hole and held into orbit. So star A, you can see, is now orbiting supermassive black hole. And so star B is then ejected out of the galaxy at a really fast speed.
Sorry.
And so yes, like I mentioned at the time, Gaia had just released their first data release, and it was huge for the astronomy community. We were all very excited. And the reason I had actually started this project is I had done research with hypervelocity stars, and I had done it on quite a few candidates, but I started to run out of data. And so I thought, well, if I can't find any more candidates, maybe I can find my own candidates for further research. And so the reason Gaia was perfect is they're very known for accurate precision of measurements of stars in the sky. And so I wanted to see if I could use that to identify stars that were moving faster compared to other stars in those regions. And so velocity components of the star, you're looking at proper motion and the radial velocity, and that using that you can find the true velocity of the star, which is what I'm looking for. I don't want to look at how, because closer stars are going to move faster. Wow, this is a presentation. But if a star is closer to you, it's going to appear to move faster than if it's farther away. So my research question was, can runaway star candidates be found in the Gaia database without use of radial velocity? At the time, Gaia didn't have radial velocity measurements for all the stars, and so I wanted to see if I could do sort of a pre-selection for runaway star candidates by only using the proper motion values. And so here I took the sky and I started to reduce it into these different sized blocks. And so I used bright ascension and declination, which are coordinate systems for the stars, very similar to longitude and latitude for Earth. And then I used parallax, which all these terms have been thrown out for the presentations, but parallax is sort of if you look at a star and you blink your eye, or if you look at, okay, pretend your thumb is a star.
Cover up my face.
And cover up.
So like, do that, cover my
And if you
face.
blink your eyes, they move. And that, using that with triangle magic, you are able to calculate the distance that a star is away from Earth. And so I sort of made these three-dimensional blocks and separated the sky because stars that are in different parts of the galaxy are going to move at different speeds, and that wouldn't help if I was looking at stars that just naturally move faster because they're in a different area. I want to find stars that are faster relative to their area in the sky. And so I did a bunch of fancy math.
Triangle magic.
Triangle magic. I don't think I'm going to go into it because it's going to be boring. But basically, I looked at combined motions that were greater than 10. Oh, and then I cross-referenced all of these candidates to two known databases because I wanted to see if there was any known information on the candidates that would either show that the method was being successful or if I found some that were already known. And so, yeah, I guess I should mention that I had coded for the first time doing this project. And so my methodology was able to take 1 billion targets, narrow it down to the 2 million that had completed calculations, because Gaia is still in process. And from the first data release, I was able to name 1,107 targets that I considered to be candidates for runaway stars or hypervelocity stars. And this is the plot of all the candidates, and as you can see, it's a lot denser near the Milky Way plane. So that was, basically this was a test to see that the selection was evenly distributed across the sky, and as you can see, it's a pretty close fit to the Milky Way plane, so I was happy to see that. Oh, and then from the candidates, I actually found on SIMBAT 332 of them had high proper motion notes, which was a good indication that my method was working to find stars that had higher proper motion, as well as 2 known high velocity stars, 2 peculiar stars. This was an interesting one I had never seen before. 9 red giant branch and 5 horizontal branch. SDSS did not have as many found in their field with my candidates, and so I found 91 cosmic ray childs and 71 galaxies. And cosmic ray child was something that had, they basically put that note on SDSS when there is a target that has moved too quickly for them to really see what it is, and so that was also a good indication because maybe these are stars that are moving faster and they couldn't see what it was. Yes. And then my hypothesis was supported because I had a lot of cross-reference data that showed that I was selecting stars that were definitely of interest, and so the method that I had chosen to use to narrow down this huge database was definitely finding stars that I was considering for further research. And this was future research, but I had done all of this already, so it's not future research anymore, but if you have any questions, you can ask me about what I continued on. This is Sadie and I at the MEDD internship. I was professional photographers take pictures of not staged work. My family. Yes.
Yeah, no questions. Goodbye. I know.
That was my first high star.
It's his mullet.
That's another mullet. I hate to say it. I know you really want it to be, but it's not.
It can be a mullet, it's the potential.
The potential. As a potential mullet, I have to study it further. Further research.
I could present my research project.
I think we're done, aren't we?
Cut over time. We're doing cut over time.
Got it? Oh, yeah, okay, here you go.
No, you know what?
Well, I'm gonna just check and see if we have a working microphone for next time.
I guess we can all adjourn back to.
What do you mean? Next year?
Check, check. We were broadcasting live on YouTube, and I guess I could stop now. Yeah, we have audio. Yeah. And let's turn that down, that down, that down. Check, check, check. Testing 1, 2.